So today in this tutorial we are going to see how to compute derivatives and also which are the applications of the derivatives, which are going to be the computation of extrema and the Taylor polynomial. So first of all you need to open the tutorial, which is already prepared. Just open it and let's put it inside the frame. So goal: how to use Maple to compute derivatives and their applications. The first section is the definition of the derivative of a function at a point, and this is just to see intuitively how or where the definition of the derivative of a function at a point comes from. So the idea is that the derivative of a function at a point is defined as the slope of the tangent line. So if you have a point and you draw the tangent line, the slope of this tangent line is going to be the derivative at the point. So how we can compute this slope? The idea is that we don't know the slope, but we are interested in point x0, but we can take another point x0 plus a distance h, a small distance, and we can compute the second line, the line passing through these 2 points. Okay, this second line of course has not the same slope that the tangent line, but if we make that this increment tends to 0, so if we approach this point, the second lines are going to approach the tangent line, and in the limit we are going to obtain the slope of the tangent line. So the slope of the second line between these 2 points is defined as using this quotient, and you can see that the point x0 is fixed, but the distance h, this increment, can vary. Okay, if the h tends to 0, then this point approaches x0. So what we have, the definition of the derivative of the function at a point is defined as the slope of the tangent line, which is the limit as h tends to 0 of the slope of the second line, which is this equation here. Just to see the animation, execute, so press intro at any point these 2 lines. Here you will have an animation where our objective is to compute the slope of the tangent line at the point 1. So to do this we take point 2, so the h is going to be 1, and we compute this slope. Okay, now since this is an animation, when we press it here at the top you get these commands. Now what we do is we make the h smaller, and as you can see the second line tends to the tangent line. So in the limit the slope of the second line tends to the slope of the tangent line. This animation can also be done using these tutorials, seconds and tangents. So we are going to do this exercise. Remember, Ctrl J, Ctrl K and F5 to change from Math 2D to 1D. Now let's see what we have to do. We go to Tutors, Calculus, Single Variable, and we're going to use tangents, but you can use both. So if we press tangents we get this tutorial. Okay, and now the exercise says that we consider the function x squared, so not x squared minus 1, at the point 1, so this is correct. If we do this display, what we get is this, and what this is saying here is that the second line has to be at a distance 3. So this is distance 1, 2, 3, 4. We want, okay, we are going to stand at a distance h2. Okay, just put it like this. Instead of 3, I'm going to do it at a distance 2. This means the point 3. Okay, I'm changing h equal to 3 to h equal to 2. So in this case we start with the point 3 and the slope of the second line is 4. If we take 2.75, the slope is 375, and for instance if we take the point 2 we get the slope 3. As you can see the slopes are all tagged into 2. We can animate this and you can see that the second line approaches the tangent line. If I reduce the step and make display, look that we are now, the maximum length is going to be h equal to 0.8, and if we make animate, we see that again the second line tends to the tangent line and that the slope is tending to 2. Now finally, if you want to reduce it and animate, you can see that the slopes are nearly 2. When you take the 0.1 and 1.05, you get a slope of 2.05. Of course, the function is x squared, its derivative is 2x, and if we evaluate 2x at x equal 1, we get 2. Okay? So just to see if it works, we define the function x squared, and we now compute the limit. We are going to do it in Math2D. The limit as h tends to 0 of f of 1 plus h minus f of 1 divided by h. This is the definition of the derivative of the function x squared at the point 1. So if you do that, you get a 2. And as we have seen in the tutorial, the slopes of the second lines tend to the slope of the tangent, which is 2. Okay? So this is like, remember that this should be a 2. This is the first section where we have seen where the definition of the derivative comes from, and now what we have to do is just how to compute derivatives with Maple. Of course, we are not going to compute all the derivatives using the definition because we don't want to compute limits all the time. So let's see how to compute derivatives with Maple. You have a lot of ways to computing a derivative. You can do it by using the commands in 1D. You can also right click on the expression using the context sensitive menus, and you can also use the palettes. Okay, so let's see the differences between them. Let's make some lines. Let's change it to F5. Now let's start defining the function. If you don't remember how to define a function, press this button here, F, tab button, X, and now x times x to the cube plus b times x squared plus c times x plus d. Okay? Now, let's compute the derivatives and the high order derivatives. First way of doing it, let's check that f of x is correct. So we place ourselves in Math2D in order to use the palette, and we type derivative of x of the function fx. This is going to be the first order derivative. Now, if we convert this to 1D, F5, copy. If I just use right click, you cannot see, but I'm using 2D convert to 1D, so you just go to the bottom, 2D convert to 1D, then what you get is the diff command, diff of the function with respect to x. And so you have two different ways with the palette using the diff command, and there's another way which is just writing the function and then using the context sensitive menus, right click, differentiate with respect to x. Okay, right click, differentiate with respect to x. So you get the three same results, this one, and this one. Okay, there's another way indeed of doing this, which is using the d command. And now I want you to look at the difference between using diff and capital D. Which is the difference of this with respect to this? The difference is that here you have an x arrow, and this is what we use to define functions. So this is the derivative as an expression, and this is the derivative as a function. So remember that if I have a function, for instance f, I can evaluate the function at a point. So I will also able to evaluate the derivative at a point. So d of f at a point 1 is the value of the derivative. If you substitute by 1 here, you get the result. If you substitute by -1, you get 3a 1 minus 2b plus c. So if we want to substitute or to get the value of the derivative at a point, the fastest way is to do this. If you just want to get the expression, you can do it any other way. What happens if you compute the derivative using the diff command and you want to evaluate it? So you can do it different ways, but one thing is using the context sensitive menus, which you right click and say evaluate at a point. We are going to put the point -1 so it coincides with this value, so you get the same result. You can see that if you want to evaluate the derivative at a point, it's easier to do directly this and not using these two lines. Okay. Now we know how to compute the first order derivative and evaluate it at a point. Let's see how we do second order derivatives. So let's go to 2D. So the second order derivative is the derivative of the derivative. Okay, so I would go here and do the first derivative of the first derivative, and then we differentiate again. So this would be the second order derivative. What would be the third order derivative? So press F5, the derivative with respect to f, the derivative, and the derivative. Remember that from one place to another you can use the cursor. Okay, so you can use as many derivative buttons as you need from the palette, and let's see how it translates it in 1D. So we right click here, again you cannot see it, but it's 2D, convert to 1D, and this one again also 2D, convert to 1D. So as you see, this means the second order derivative is the derivative of the first derivative, and the third order derivative is the derivative. First we differentiate once, then again, and then again. There's a way of simplifying this in Maple, which is if we want to compute the third order derivative of a function, we can just choose, this is the first order derivative, we can just add x's at the rear. Okay, so this would be the third order derivative, fourth order derivative, and etc. Okay, so there's no need of doing this, as you don't have to write diff as many times, but you can do it in this way. Okay, so now what about if I want to evaluate the second order derivative, at a point? So I would use again the context sensitive menus, evaluate, and I would take for instance a point 2. So this would be the value of the second order derivative at a point 2. Now there is another way of computing higher order derivatives, which is by using the D command. Look at this. This means the first order derivative of f. If I change the 1 by 2, this is the second order derivative. If I change it by 3, this is the third order derivative. The advantage now is that these are functions, so they can be evaluated. So what I can do, F5, is this is the second order derivative, and I can evaluate it at 2. So if I want to compute the second order derivative evaluated at a point, it's far faster doing this command or using this command instead of using these other two commands. Okay, so this is mainly all the ways that you have to compute derivatives. You have a lot of ways, and all of them yield the same result. It depends on how fast you want to go. You use one or another. Now here we are going to have a look at a tutorial which is not going to be used to get the direct result of a derivative, but to learn how to compute derivatives. Okay, so let's enter the tutorial, which is Tools, Tutors, Calculus Single Variable, Differentiation Methods. And now let's consider, for instance, this starting function x times sine of x. What do we have to do to compute this derivative? We can ask for a hint, and it says notice the multiplication in the expression. So they mean that something is related to the product. So if we go to the product, here you will see the formula the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. So if I do product, I get the derivative of the first function times the second without the second plus the first function times the derivative of the second. If I do next step, the derivative of x is 1. If I do next step, the derivative of the sinus is cosinus. Okay. Let's see now what happens with sine of x divided by x. Let's start, and if we get help, it says notice the division in the expression, so we have to use the quotient rule, which says that the derivative of a quotient is the derivative of the first times the second minus, the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the denominator square. So if we do that, next step, you see that the derivative of the denominator times the denominator minus the derivative of the denominator times the denominator divided by the denominator square. Now, if we apply next step, we get that the derivative of x is 1, and then the derivative of sinus is cosinus. Okay? So here you can learn, you can copy this and go to the tutorial if you want, but you can also compute, for instance, the exponential, the derivative of the exponential of the cosinus of x. In this case, if you do get hint, notice the chain in the expression, the chain rule, la regla de la cadena. So if we apply the chain rule, remember that this is, if we have a composition of functions, the derivative is going to be the derivative of e, the exponential function, applied to the cosinus times the derivative of the cosinus. If we do chain rule, we get the derivative of the first function evaluated at cosinus times the derivative of cosinus. If we do next step, it says which is the derivative of the exponential is itself, so e elevated to the cosinus of x times the derivative of the cosinus, which is minus sine of x. Okay, so now you could copy this, close, come here in the tutorial and paste it. Okay, so this tutorial is mainly to study, because if you want to compute the derivative of this function, you would use the d command or the diff command directly. So this is just to study and to see if the steps you are following are correct. Okay, so now that we know how to compute derivatives, we are going to look at its application, which is the computation of extrema, maxima and minima, and also the Taylor series expansion. So let's start with the extrema. One of the applications of derivatives is the computation of the extrema or inflection points of a function inside an interval. So how do we compute this extrema? First we have to find the candidates, and the candidates are the points where the function is not continuous, the points where the function is not differentiable, points with zero derivative, and the ends of the interval. Okay, once we have the candidates, we just have to study the sign of the derivative to see the behavior of the function around the candidate. If the function, for instance, is increasing to the left and decreasing to the right, it means it's a maximum. If it's decreasing to the left and increasing to the right, it's a minimum. And if it increases or decreases to both sides, it's an inflection point. So also remember that you have this tutorial which directly tells you how to compute the maximum minima. So let's start using the tutorial F5. Well, let's first define the function. Remember that you can press this button, f x. So the absolute value of x minus 3 times x squared times 6 minus x. And now, since we want to enter the tutorial, sorry, what am I doing? We are going to type the expression, okay? And now what we want to do is use this tutorial in the interval minus 2, 7. So tools, tutor, single variable, curve analysis. So we open this. Oh, I forgot to copy the function, so I will close again. Okay, sorry for this. Copy the function, Control C, open the tutorial. Now we paste it, minus 2, 7. So display. This is the function we are going to study. So using this plot, you can see that here we will have a maxima, the absolute maxima, 2 local maxima, and then 2 local minima, an inflection point. Well, no, this is a 0, sorry. And we're also going to have an absolute minimum. Okay. So now we can copy the local maxima and close. I'm going to paste it here. I'm going to use text, well, Control T, and I'm going to place the maxima. And in order to enter the tutorial without having to type it again, I'm going to just put that we are going to study f of x between minus 2 and 7. This way I don't have to put it again. Now I'm going to put minima. Calculate. I'm going to copy the minima below. So this is the fastest way to compute maxima and minima, the extrema. But the problem is that you get information with really low decimal places, 1.83. What about if you want to have 5 correct decimal places? So in this case, you have to do the study by hand. Okay, so let's see how we do it by hand. Let's take all these lines, which is the candidates, and let's start. So what I'm going to do is I'm going to type it here, Control B, and now here I make Control J to insert some lines. Study the points where the function is not continuous. Remember that we have a command which is iscont, which helps us know if a function is continuous or not. So you copy the example and then we study it, F5. We are asking if the function f of x is continuous, and in our case it's between minus 2 and 7. And it says that it's true, that the function is continuous. So here we don't get any candidate in this section. Control J, sorry. Now, points where the function is not differentiable. With Maple, instead of using the definition you use in class, we are going to look at the continuity of the derivative. If the function is not derivable at a point, then the derivative is not going to be continuous. So what we are going to do is ask if the derivative, so I'm going to include the d here, is continuous. So it says it's false. So probably there's a point where the function is not differentiable. How do we compute the points? So we use the command iscont. So if you go to the command iscont and copy, this command tells you where the discontinuities are. Instead of 1 divided by x, we have this function. Sorry, we are not going to look for the discontinuities of the function, but about the derivative. Okay, so here we have x equal 3 is a candidate since f is not differentiable in this point. Okay, if you look at the plot, you can see that this here we have a peak. So having a peak, so the slope from the right and the slope from the left and the slope from the right does not coincide. So this is a point where the function is not differentiable. So we already have one candidate. Now, points where the derivative is 0. So what we want to do is solve this equation. Derivative of x equal to 0. And this can be done really easy using the context sensitive menus. You just right click. Let me do more spaces here. You just right click, solve, solve. So when asking for solve, the solve command, we get 3 candidates. You can also evaluate this, Control C, Control V. Okay. In order to put it in decimal places, you just need to put one of the numbers in decimal places. And now the second number it's going to be this one. So we have 3 candidates here. You can see that these are the same numbers we got here, but with more precision. Okay, so here what we get is x equals 0. I'm going to put it more or less 4.92 and 1.82. Okay, so you get 3 candidates which have 0 derivative. We can go up. This has a 0 derivative. This 1 point, it also has the tangent line which is horizontal, and then 4, it also has this line which is horizontal. So these are the 3 points. And then of course here we get x equal -2 and x equal 7. So to summarize, the candidates are, let's see, the first one is 3, a point where the function is not derivable. Then we get 0, this one here, Control T, and this one here, and Control T. We also have -2 and 7. So we have 5 candidates, and now we should study if we have a maximum or a minima. Okay, so let's start seeing one of them. So let's see that the point x equal to, let's get this one without the point. What do we have to see? This point is the 492. 492 should be a maxima, local maxima. Okay, so it's a maxima. So what do we have to do? We define the point. Sorry, let's do it in 2D. We define the point. We just can copy it and paste it. It's not a problem. Well, it is a problem, so let's copy it. Let's see if we can copy it from here. Okay, so we get the point, and now what we are going to do is to compute the derivative at this point, but a little less, the left of the point. Okay, so now you see that we don't get the result in numerical value, so we use eval. So the derivative on the left is positive, it means that the function is increasing, and the derivative on the right is negative, so it means that the function is decreasing. So positive on the left, negative on the right, it means a maxima. Now what you can do is to change this point if you want to just do it again. So you can put a minus here. The value that is going to maple is going to use is the last one you have executed. So at this point we have this value. You can also check it by just doing eval xgen. So now what we are looking at is the 1.8. At the left is positive, at the right is negative, so again it's a local maxima. So we have, these numbers are 2 local maxima. And then if we go for the 0, for instance, we now have 0. On the left is negative, on the right is positive. It means decreasing on the left, increasing on the right. It means a minima. Okay, so you can do it again with the number 3 or with all the candidates. Now once you get all the candidates and you know that what they are, so here we have a maximum, minima, maxima, minima, maxima, and minima. Then in order to get which are the absolute extrema, you just have to evaluate the function at the points. So for instance, f of x, for instance, the absolute extrema are found making a table of values. For instance, let's see, f of 0, f of -2, f of 7, and now we also need f of 3, and sorry, jj. What else? We need f of this point here and f of this point here. f of this point here and f of this point here, and also we need to evaluate this, so we make a point 0 or use the evalve command. So from all these values, which is the maximum value? -2, so this would be the absolute maxima, and the minimum is -196, which means that this is a minima. Okay. One thing that I didn't explain is how to put more than one line is by using Shift Enter. Instead of pressing Enter, you use Shift Enter, and then you can introduce more than one line in one command line. Okay. So now you know how to compute maxima and minima. You can use the tutorial to get an initial idea of what you will get, and then you will have the values but with low accuracy, and then what you can do is to compute them by hand to have the numbers with much more precision. Okay. Now once we've seen how to compute the extrema, let's see how to compute the Taylor polynomial and what does it mean. The Taylor polynomial is used to approximate a function by a polynomial. Why is it used? It's used for a lot of things. Imagine that you have a function which you have to integrate, and the computation of this integral is really complex. So the idea, what you can do is to approximate the function by a polynomial and then integrate this polynomial. Of course, if the function and the polynomial are pretty close, the two values of the integrals are going to be close also, and integrating a polynomial is trivial. Okay, so the other thing is that we are going to approximate a function by a polynomial always around a point, so it will give an approximation around the point we are working now with. So now the expression of the Taylor polynomial is here. The polynomial approximating the function at point x0 is the value of the function at x0, the first derivative evaluated at x0 times x minus x0, the second order derivative divided by 2 factorial times x minus x0 squared, and then you can go on up to the order you need to compute. You can also compute it here in Maple using the Taylor command, which is faster, and also using a tutorial. So let's start with this exercise. Remember F5 all the time. We just, if you don't remember how to put functions, you press this 1 divided by x, which is going to be the point. The point is going to be x0 equal 1. And then they ask to compute a polynomial of degree 3, a third order degree polynomial. So let's start with the definition. Okay, I need to compute f of x0. This would be the 0 order polynomial. Then the derivative evaluated at x0, so I use the d because it's faster, times x minus x0, x minus 1. So now I get the tangent line at point x0. This is the tangent line at the point x0. So the first order polynomial, Taylor polynomial, coincides with the tangent line. If we compute the parabola, we have to change this by the second order derivative divided by 2 factorial times x minus x squared. This would be the parabola, and we are asked to compute the third order derivative, third order Taylor polynomial, so we add an extra term, third order derivative divided by 3 factorial x minus x0 to the power 3. Okay, now we can simplify this expression. Simplify, again you cannot see it, but it's simplify, and we get this polynomial. So this would be how we would compute this by hand. Let's use the Taylor function. Taylor of a function, in this case f of x, at the point x equal 1, and the order. If I put 3, you can see that I get a second order polynomial plus a term which is strange, is order of. So always when you want to compute the Taylor polynomial of order 3, you have to add a plus 1. So you have to compute it up to order 4. Okay? And now, as you can see, this is not a polynomial because we have this expression here. So what we have to do is to convert this equation 4.5, Control L to insert a label, 4.5 into a polynomial. Okay, So when we use this command, what we see is that we get the same expression we got without the O. So if we want to use the Taylor polynomial as a polynomial, we have to use the convert. And now if I want to simplify it, I'm going to simplify, Control L, equation 4.6, and we get the same results. Okay, so you now have two options to compute the Taylor polynomial: by hand or by using the Taylor command plus the convert. And the only thing you need to know is that you have to use one or more. Let's see now what about the tutorial. So tools, tutors, single variable, and Taylor approximation. So here we are going to enter 1 divided by x. The point is going to be 1, and the degree is going to be 3. So if we look at it, you get the same result we got here. Okay, the Taylor polynomial is this one, but you also get a plot. You can see that the function and the polynomial are really close, around 1. I'm going to show you, this is the second line, the tangent line, 2 minus x is what we got here. The first one, 2 minus x. You can see that this is quite close to the function, but if I increase the polynomial, you see that every time I increase the polynomial, the function and the polynomial are closer, around 1. Far from 1, they are not the same. So this polynomial is closer to the function around the point. So you can increase this as much as you can, don't go that far. Okay, so as you can see, around the point you get functions which are really, really close. Okay, now what you can do is you do the third order polynomial, you copy this, Control C before closing, and then Control T, and you can paste it. Okay, so now let's see why or how near the Taylor polynomial stands for the function. So let's first define the polynomial. Let's copy this. Let's compute the Taylor polynomial using the Taylor function, and we are directly going to convert them to a polynomial. Okay? Instead of using two lines, I'm computing the Taylor polynomial and then converting it. Okay, so this is the polynomial, and I'm going to call it this p. P is going to be equal to the polynomial. Okay, now what about if I evaluate the function at 1.01? So this is the third order polynomial. How close are the value of the function and the polynomial? F of 0.1 is this value here, and then if I substitute the value x 1.01 to the polynomial, you get a value is quite close. The error we are committing is just the difference between the exact value minus Control L, the approximated value. This is the error, which is of the order 10 to the minus 9. If I now take a point which is further, 1.1, you get that we also get a good approximation, but the error increases. Okay, and if I take the point 2, so you can see clear here that the difference is larger, the error is 1/2. Okay, so the error is 1/2. But if I take values close to 1, if I take 1, they both coincide, so the function and the polynomial at the value 1 execute are the same. But if I take a point quite close, I can get really good approximations. So as I approach the point 1, the approximations are closer. Okay, so that's what we use the Taylor polynomial for, to approximate a function around a point. Okay, so now let's do the following exercise. which is approximate the number e doing an approximation of the function exponential of x around the point x equals 0, okay, and take a degree for the Taylor polynomial high enough to get a good approximation, so the error, small error. Okay, so let's do this. We define the function, which is going to be the exponential of x, and now we define the point x0 equal to 0. Okay, now I can compute the Taylor polynomial f5, Taylor of f of x around x0. Sorry, this is not a function, always the same mistake. In order to be a function is f of x. Okay, and I want to convert it to a polynomial. Okay, and I'm going to define it by p. Now, if I don't say anything, I get a 6 or 5 for the polynomial. Let's start with degree 2. Remember that degree 2 is a straight line because we get one less. So now, what is the value of f of 1? F of 1 is the number e, so if I get 1 point, is 2.75. Let's see what happens if I say substitute x equal to 1 to the polynomial. What I get is an approximation which is 2. So the error is going to be Control L 4.15 minus Control L 4.16. The error is 0.7. So if I approximate the exponential function by a straight line, I can approximate the e value by a 2. Note that substituting this polynomial by 1, it's really easy. So let's increase and compute a parabola. Now, what will be the approximation when we substitute x to 1? It will be 1 plus 1, 2 plus 1 half, 2.5. If I now repeat the substitution, the error is going to decrease. If I now take a third order polynomial, remember that this is 3 plus 1, the approximation will be 1 plus 1 plus 1 half plus 1 over 6. So I'm going to get 2.6, which the error is going to be 0.05. So if I increase this, the approximation is going to be 2.7, which is going to be a small error. So the idea is that we can compute the Taylor polynomial, and to evaluate f of 1, I need a computer, because I don't know how to compute the value e without a calculator or a computer. But now, if I give you this polynomial, you can evaluate it at 1 and do the computations by hand. So let's increase it a little bit more, and you will see that the error is decreasing. So just by substituting here by 1, you get a really great approximation of the number e. Okay, and if you want to look at how many terms you need to compute the same number, so we go to order 11, and we just get the same exact result with Maple. Okay, so just by substituting here by x equal 1, you get the same result. If we use the Taylor tutorial and we introduce the exponential function around 0 and we compute degree 1, what we are doing is trying to compute the function at point 1. So of course the value of the polynomial and the value of the exponential function here are very different, but if I increase to a parabola, you can see that the value of the function and the polynomial at 1 are quite close. Now here, if I take a polynomial of degree 3, I cannot see visually the difference between these both two values. And if I increase, you can see that the function and the polynomial at point 1 are going to be closer and closer and closer, okay? So, if you, for instance, if we want to compute an approximation of e to the power 2, e squared, here you can see that you would get a quite good approximation because in view the function and the polynomial are quite close. Okay, so let's put a 3 here and let's close it. Okay, so now you know all about derivatives. What you just have to do now is to try to do these exercises, self-evaluation exercises. You have here 4 exercises regarding derivative, extrema and Taylor, and then here you have 3 more exercises, up to 7 exercises. So that would be it for today. Try to do the exercises and ask anything you don't understand.